Howdy. We are back now to talk about double angle identities. I know you've just been waiting on pins and needles for this, right? Actually, double angle identities, they flow right away from our sum and difference identities that we did previously. Previously we learned that if you had like the sine of alpha plus beta, that equaled sine of alpha cosine beta plus cosine alpha sine beta. But what if alpha and beta are equal? Alright, let's replace with theta and see what happens. So let's say we have sine of theta plus theta, which is essentially sine of 2 theta. Then we would have sine of theta cosine theta plus cosine theta sine theta. Whether you say sine first, cosine second, or cosine first, sine second, doesn't really matter. So what we really have here is 2 sine theta cosine theta. That's one of your double angle identities. Woohoo! So there's that. Okay, well, the same idea. Let's take our cosine of alpha plus beta. We know that equals cosine alpha cosine beta minus sine alpha sine beta. And let's replace with theta. Let's do cosine of theta plus theta, or cosine 2 theta. We're going to have cosine theta minus sine theta sine theta. So that's the same thing as saying cosine squared theta minus sine squared theta. Ooh, there's another one of our double angle identities. Alright, what if we take cosine 2 theta and play with it a little bit? Let's say we replace cosine squared theta with 1 minus sine squared theta. So instead of cosine squared theta right here, we have 1 minus sine squared theta. Well then, cosine 2 theta is 1 minus 2 sine squared theta. And that's yet another one of our double angle identities. Or rather, what if instead of replacing cosine squared theta, what if we replace sine squared theta with 1 minus cosine squared theta? Then we've got cosine 2 theta equals 2 cosine squared theta minus 1. So yet another one of our double angle identities. We got a bunch of them. So we got sine of 2 theta is 2 sine cosine. Then cosine 2 theta, we got a couple of variations. You can get the cosine squared minus sine squared, but then you can vary it by replacing with that Pythagorean identity. Alright, and then what about tangent? We had the tangent of alpha plus beta. We knew that it was the tangent alpha plus tangent beta over 1 minus tan alpha tan beta. So same idea, what if alpha equals beta? So let's replace alpha and beta with theta. So we're going to end up figuring out what tan of 2 theta would be. So we got tan theta plus tan theta over 1 minus tan theta tan theta. So basically we end up with 2 tan theta over 1 minus tan squared theta. And there's the double angle identity for tan. Okay, so there's our double angle identities. Now let's take these and see some problems that we might have to do with them, like see where they might come in useful. Okay, let's start out with, what if we're given that the sine of theta is 8/17 and that cosine theta is less than 0. And we have to find sine of 2 theta, cosine of 2 theta, tangent of 2 theta. Alright, first of all, if the sine is positive and the cosine's negative, A smart, up here, let's see, A and everything's positive, smart, sine's positive, cosine's negative. So we're looking at over here somewhere. So our theta is here. If the sine is 8/17, that means opposite is 8, the hypotenuse is 17. And if you go ahead and do a little Pythagorean theorem here and solve for the missing side, you're going to get negative 15 for this side. You get 15, but it's negative x-axis, so it's negative 15. Alright, so with this, we know the sine of theta is 8/17. We know the cosine of theta is negative 15 over 17. And we know the tan of theta is negative 8/15. Okay, so knowing all that, let's start with sine of 2 theta. Sine of 2 theta is 2 sine theta cosine theta. So it's 2 times 8/17 times negative 15/17. If you go ahead and multiply all that together, you get negative 240 over 289. Alright, next we'll find cosine 2 theta. We know that equals cosine squared theta minus sine squared theta. So we can do negative 15/17 squared minus 8/17 squared. So we're going to end up with 225, and we're doing a minus, and we're going to end up with a 64 in the numerators, and then 17 squared will give us 289 in the denominator. So we end up with 161 over 289. Alright, finally, tan 2 theta, we know is 2 tan theta over 1 minus tan squared theta. So we got 2 times negative 8/15 over 1 minus the negative 8/15 squared. So we got negative 16/15 in the numerator. Then we have 1 minus 64 over 225 in the denominator. So we got the negative 16/15 in the numerator. Denominator, 1 is really the same thing as 225 over 225. So we're dividing by, what, 161 over 225. So we got negative 16/15 times 225 over 161. Do a little reducing right here. And we get negative 240 over 161. So we're able to go through and find the sine of the double angle, the cosine of the double angle, and the tan of the double angle, just knowing that what the sine was and that the cosine was negative. Just knowing those two pieces of information, we're able to find all those double angles now. Alright, another way this could be given to us is we could be told the double angle. Like we could be told cosine 2 theta is negative 12/13, and then we might be told just where theta lies. Alright, so if theta is between 180 and 270, then theta is somewhere in here in quadrant 3. Twice that though, 2 theta, twice 180 is 360, and twice 270 is 540. So 2 theta is going to fall somewhere in here. But then knowing that the cosine of 2 theta is negative, that narrows it down that 2 theta has to be in quadrant 2 somewhere. Okay, that's nice to know. So, if 2 theta is in quadrant 2 somewhere, and cosine 2 theta is negative 12/13, let's see what we got here. Could draw a triangle here for the 2 theta scenario. Maybe work with that. Let's see. Using this, let's find all 6 values here. Find all 6 trig functions. Of theta. Alright, now we know that cosine 2 theta is the same thing as 1 minus 2 sine squared theta. So let's use that to try to solve for sine. So 1 minus 2 sine squared theta has to equal negative 12/13. So negative 2 sine squared theta must equal negative 25/13. So sine squared theta must equal 25/26. Now since theta is in quadrant 3, a smart trig, the only tangent's positive here in quadrant 3, so we're going to do the negative square root because of the fact that we're in quadrant 3. So we got negative 5 over the square root of 26, or negative 5 square roots of 26 over 26 for sine theta. And once you know sine, you can do cosecant. It's going to be negative square root of 26 over 5, because it's the reciprocal of sine. So there's 2 of them, 2 down, 4 to go. Okay, we also know that cosine 2 theta equals 2 cosine squared theta minus 1. So let's do that. It's 2 cosine squared theta minus 1 equals negative 12/13. So 2 cosine squared theta equals 1/13. Cosine squared theta equals 1/26. Okay, again, we're in quad 3 for theta, so cosine is negative there. So we'll do the negative square root. So cosine theta equals negative 1 over the square root of 26. Which means cosine theta equals negative square root of 26 over 26. So there's another one of our trig functions. And then secant theta is the reciprocal of that. So we're going to have negative square root of 26. All right, and then finally, tangent is sine over cosine. We found sine to be, let me go ahead and just use the negative 5 over square root of 26. We found cosine to be negative 1 over square root of 26. So tan is going to be reduced down to 5. And cotan is reciprocal, so that's going to be 1/5. Okay, so you're able to use a little bit of information here. Just the fact that cosine 2 theta is negative 12/13, and basically the quadrants narrow down from theta being between 180 and 270. You're able to look at all that information and narrow it down as to where your theta has to be located, what quadrant, and then go through and use your identities to solve for all 6 trig functions. Okay, what's another situation? Another situation, you might be asked to take some expressions and simplify. You might be asked to simplify an expression. So you might have something like 2 cosine squared 5x minus 1. Well, that fits the cosine of 2 theta format. So you got cosine of 2 times 5x, or cosine 10x. Or you might have something like sine of 165 degrees cosine of 165 degrees. And you know that sine of 2 theta is 2 sine cosine. They gave you sine cosine, so this is going to equal 1/2 sine of 2 theta. So 1/2 sine of 330 degrees. So you have 1/2, and the sine of 330 is going to be negative 1/2. So you get negative 1/4. Or it might be given to you like this. They might say, write cosine 3x in terms of cosine x. Something like that. Well, cosine 3x, you could rewrite it as cosine of 2x plus x, turn it into a cosine of a sum. Then using your identity you learned previously, you got cosine 2x cosine x minus sine 2x sine x. Gotta get everything in terms of cosine x, so we gotta see how we can rewrite all this. Well, cosine 2x, we could use 2 cosine squared x minus 1. And then you still got cosine x there. If you go ahead and distribute, you get 2 cosine cubed x minus cosine x. And then let's see, sine 2x we know to be 2 sine x cosine x. I don't know why the pen keeps doing that. And then you got that other sine x still sitting there. So basically you got minus 2 sine squared x cosine x. But sine squared can be replaced with 1 minus cosine squared. So then you got 2 cosine cubed x minus cosine x. And then you got minus 2 times 1 times cosine x will give you minus 2 cosine x. And minus 2 times minus cosine squared x times cosine x will give you plus 2 cosine cubed x. Combine any like terms, you got 4 cosine cubed x minus 3 cosine x. So now it's all in terms of cosine x. No longer any cosine 2x or cosine 3x. Even this cosine cubed x, that's like saying cosine x cubed. So everything's in terms of cosine x now. Alright, well, that's your double angle identities, and that's also some situations where you're going to use them to simplify or manipulate or verify, those kinds of things. And then these double angle identities will be a nice springboard into looking at the power reducing formulas and half angle identities. So that's where we'll head next. Thank you for joining us.